We will continue our discussion on FM receivers today. We will complete our discussion on pre-emphasis and de-emphasis and spend some time on stereo broadcasting using frequency modulation. So, if you may recollect, we had looked at the effect of interference, sinusoidal interference or tonal interference on the performance of PM and FM receivers, right. And what we found was that if you look at the amplitude of the interference output as a function of the input interference frequency, for the case of phase modulation this amplitude was constant, equal to some value, some AI by AC or something, right. For the case of, this was the case for PM. For the case of excuse me please, for the case of frequency modulation this amplitude increased linearly with frequency, and we therefore argued a case for putting at the receiver a filter which would attenuate the interference frequencies of the interference amplitude at the higher frequencies at the output, right. So, we said that we will use a low pass filter at the receiver which will attenuate the higher frequencies, so that the interference due to the higher frequencies in terms is reduced, and the overall response curve for the FM case after introducing this filter at the output of the discriminator, right. So, this is a low pass filter which we call the de-emphasis filter, right. The overall response curve would be something like that. The cutoff frequency here is selected in such a manner that you get a response like that. This cutoff frequency, which we call f sub 3, we said should be typically less than W, where W is the bandwidth of the message signal, right. However, as somebody rightly pointed out, since you are going to have at the output of the discriminator a filter like this, it will also distort the signal itself, because this cutoff frequency is below the bandwidth of the signal, right. So, there will be some components of the signal which are higher than the frequency f sub 3 which will get attenuated as a result of this, right. So, to counter this effect we use a so called pre-emphasis filter at the transmitter, whose characteristics are opposite to those of the de-emphasis filter. So, suppose the de-emphasis filter has a transfer function, let us call it H sub df, okay. So, then the pre-emphasis filter and the de-emphasis filters must satisfy this condition. The pre-emphasis filter transfer function HPF into the de-emphasis transfer filter transfer function should be equal to 1. They should not cause any distortion, right. Their product should be equal to a constant. Sorry? Well, whatever it is, question is whatever the transfer function you have here, the transfer function HPF should be such that over the frequency band of interest, that is from 0 to W, the product should be a constant, right. In particular that will be directly yes affecting this particular region, right, because in this region it is anyway constant more or less. So, for mod of f less than W. So, basically what you are saying is your FM system now looks something like this. You have a message, look at both the transmitter as well as the receiver. So, the message signal MT, instead of being sent to the frequency modulator directly, is first pre-distorted, right. it is pre-distorted to take care of the fact that there is a de-emphasis filter which otherwise will distort the signal, right. So, it is pre-distorted by using a pre-emphasis filter. Right, and this has a transfer function. This filter has a transfer function. It's a PF. The output of this filter is the one which is sent to the FM modulator. Okay. And this is what is transmitted. This is what is broadcast. At the receiver, you have your limiter discriminator. It is limiter, band pass limiter. You have your FM discriminator, and finally you have your de-emphasis filter. With the transfer function of H sub df, and that should hopefully produce an undistorted message empty. Okay. So, the job of the pre-emphasis filter, the job of the de-emphasis filter was to attenuate the high frequency interference that would come out with large amplitudes at the discriminator output, right. The job of the pre-emphasis filter is, okay, because of that, since the high frequency components of the signal also get attenuated, you emphasize or amplify the higher frequencies of the signal, high frequency components of the signal, right. So, that is basically what you will tend to do. When you do that, there is a slight side effect in as far as the modulator is concerned, because if you remember, the peak frequency deviation will depend on the amplitude, particularly in the case of FM, amplitude of the higher frequency components more, right. So, the peak frequency deviation may slightly increase as a result of this, but that is hardly a major problem to worry about, right. Since signals typically otherwise, if you take for example an audio signal or a voice signal, the higher frequency components are slightly lower in strength, right. So, one has to therefore guard against the fact that you are further attenuating them at the de-emphasis by using the de-emphasis filter. So, you must amplify them slightly at the transmitter itself, so that the effect of the de-emphasis filter is taken care of. So, we will have reason to come back to pre-emphasis and de-emphasis filters once again, and these methods of improving the performance of FM receivers once again when we discuss effect of noise later on, right. Okay, let us move on, and let me talk a little further on FM receivers. You are all familiar with FM broadcasting these days, in radio for example, and you all know for example that the frequency band is, do you remember, 88 megahertz to 108 megahertz, right. Typically, if you have multiple FM transmissions taking place in a region, right, of course in our country, in the city of Delhi, I do not think we have too many FM broadcasting stations, we only have 2, right. But if you have multiple broadcasting stations in the same neighborhood, you like to ensure that the transmission frequencies of each of these stations is well separated, right. And how much should the separation be? Let us make an estimate. We mentioned that the peak frequency deviation in typical FM, commercial FM transmission is of the order of 75 kilohertz, right. So, the approximate bandwidth, suppose you are transmitting music, its bandwidth is about 15 kilohertz, right. So, the approximate bandwidth of the FM signal would be twice into 75 plus twice into 15, that will come to about 180 kilohertz, right. So, that means successive transmission station should be separated from each other by about 200 kilohertz, taking about 20 kilohertz as a guard band, right. So, typical separation between various transmitters. So, separation of carrier frequencies will be of the order of 200 kilohertz. Okay. This is as far as monophonic receivers are concerned, that is single channel receivers. Typically the IF frequency in the receiver, the intermediate frequency is of the order of 10.7 megahertz. In fact, this is the standard. 10.7 megahertz is the intermediate frequency. Remember the concept of intermediate frequency in a super heterodyne receiver. So, the concept of super heterodyne receiver is equally valid for SM receivers also. Whatever we do for AM receivers is also carried over to FM receivers. All the advantages of a super heterodyne receiver would carry over to the FM receivers, right. Okay. Let us next come to stereophonic FM broadcasting. In fact, FM is most popular in carrying out this kind of broadcasting. Basically, it is used for transmission of high quality music, and it is usually done to also capture not the simple monophonic effects in a music environment, but also the stereophonic effects. I hope you all appreciate what a stereophonic effect means. Basically, it implies that you are trying to discriminate the music that you are listening on the basis of their spatial distribution of music rather than just the temporal waveform, right. You are of course ultimately interested in the temporal waveform, but you also want to differentiate spatially as to which instrument is playing in which relative to each other in what spatial location, right. So, basically therefore, you need to have multiple sensors at the time of recording the music or at the time of picking up the music. Rather than a single microphone, you will have distributed microphones in space, right. And typically you can use as many as you like, of course, and depending on the cost that you can bear, but typically in stereophonic systems you have at least two sensors which are fairly well separated from each other to pick up the signals from, let us say, the left and right of a performing stage, right. And then you have to send both the signals together and feed these signals to the appropriate speakers, so that you can keep the spatial discrimination possible. Okay, that is basically the idea. So, the sense as far as we are concerned, as far as FM transmission is concerned, the implication is that instead of transmitting one signal, you have to transmit two signals, right, both the left signal as well as the right signal, right. So, the way we do it, I will just describe that, but before we describe what we are going to do, you must also appreciate that when you do stereophonic, of course this question is a little irrelevant today, because today I think most FM radios would be stereophonic FM radios, but when these standards are formulated, when they were formulated in the first instance, there were FM stations, FM broadcasting or FM receivers which were not meant for stereophonic broadcasting, because FM broadcasting in the first instance was not stereophonic broadcasting, it was monophonic broadcasting, right, transmission of a single signal, right, which is just picked up. So, these two systems must be compatible with each other. Even if you are transmitting a stereophonic broadcast, a monophonic receiver should be able to pick up the signal in the way it should have heard otherwise, right. So, stereophonic FM broadcasting is therefore made compatible with a monophonic receiver, right. So, how that is done and how the stereophonic broadcasting is done is something that we will discuss now. It is a very simple thing, we will soon see. It is really very simple system, but this system uses many of the concepts that we discussed till now, and that is why I want to spend about 5 to 10 minutes on this. Let us look at the transmitter first. As I said, for spatial discrimination of the signals, for spatial discrimination, let us say of signals as in music, we like to pick up two signals which we call the left signal and the right signal, and we do not transmit them as left and right. We have a matrix which combines these signals into two other signals. One is called L plus R, the other is called L minus R, right. So, here plus minus and here plus plus, and the reason why we do that is because for a monophonic receiver it is the L plus R which is relevant. You want to look at the total signal for the left from the left half part of the stage as well as the right half part of the stage, right. So, you want to look at both the signals together. So, this is a signal which is of interest to the monophonic receiver. Both the signals are of interest to the stereophonic receiver, from which of course you can reconstruct L and R by again subtraction and addition, right. So, that is easy. Now, we must send this through a pre-emphasis filter, both the signals. Now that we have discussed the role of pre-emphasis, we do that. And remember, another constraint that we have to have the receiver is that we must be able to separate these two signals in the receiver, because before we transmit we will have to somehow combine them, right. But the combining process of these two signals, ultimately we have to transmit only one signal. We will not actually transmit two signals, two FM signals, right, but we must transmit them sufficiently separated from each other in some sense that we are able to separate them at the receiver. We must have an L plus R and an L minus R available. How can we do that? How should we transmit simultaneously L plus R and L minus R? We have to transmit two signals now. So, we have to use one of the multiplexing techniques, right. Typically we do what is called frequency multiplexing here, right, frequency domain multiplexing. We transmit L plus R in the baseband, and we keep L plus R in the baseband, but L minus R is shifted up in frequency, right, before we do any FM. This is done just to make sure that we continue to have separate entities available. Is it clear? So, we have therefore a DSB-SC modulator here, which has some carrier frequency FC prime, right. I will call this signal L minus R prime signal, because L minus R after pre-emphasis. So, I will just call it L minus R prime, and these two signals are added together. And transmitted. Now, so since we are doing a DSB-SC modulation here, right, because of the fact that we have a carrier coming here, we just want to do a frequency multiplexing. We are shifting up this signal by an appropriate amount. Let me also tell you the frequency that is used. Remember, your baseband signal has a bandwidth of about 15 kilohertz, because we are talking music kind of signals here, right. So, the DSB-SC signal around FC prime would go up to FC prime minus 15 to FC prime plus 15. So, I like to make sure that FC prime minus 15 is well above 15 kilohertz, right, so that the two do not overlap, right, and the standard frequency which is used for this purpose is 38 kilohertz. The carrier frequency, we call it a pilot, we call it a sub carrier, right. This is not the final transmission. Although I said this is transmitted, but this is not transmitted as such. So far there is no frequency modulation, right. So there is a sub carrier of frequency 38 kilohertz, which is used to DSPSC modulate the L minus R signal. Okay. Now since we are using a DSPSC modulator, what kind of demodulator we will have to have at the receiver for separating this out back? We will have to have synchronous receiver for this purpose, right, which means I must transmit this pilot carrier, must transmit a signal by which I can extract the carrier properly, right. However, I do not do that, I do not transmit a pilot carrier of 38 kilohertz because that is a little more difficult to separate out, as we will soon see. What we do is we generate this 38 kilohertz at the transmitter by using a 19 kilohertz oscillator, right, and a frequency doubler. So you generate 19 kilohertz, do a frequency doubling and transmit this, and this signal 19 kilohertz signal is also added on to the transmitted signal. So the signal that you actually, the message that you actually transmit is the L plus R signal. It is the L minus R signal with a frequency shift of 38 kilohertz, right, DSPSC version of that, and this sub carrier at half its frequency, right. These three signals form a composite signal. So there is a composite signal which contains these three components, and this becomes your basic message signal for the frequency modulator. Okay. So you have an FM modulator finally. So the FM modulator works on this composite signal and transmits this. Of course, baseband signal bandwidth, this, if you think of this as your baseband signal, the spectrum of your baseband signal will look something like this. Let me draw the spectrum. Your composite signal has this kind of spectrum. Let us say this is your L plus R signal, right, goes up to, I am only drawing one side of the frequency axis, there will be symmetry on the other side of the frequency axis. Okay. Then this same signal L minus R, not the same, this is L plus R prime, L minus R prime is a DSPSC signal, right, with a center frequency of 38 kilohertz, and the pilot carrier is somewhere here at 19 kilohertz. So that, yes, so that it is very easy to pick out the pilot carrier and pass it through a phase lock loop to get a synchronous carrier, right. We seen that the phase lock loop can be used to acquire a carrier, input signal carrier, right. So since this is, so if I have a band pass filter, we just extract this pilot carrier, pass it through a phase lock loop, I will get a clean version of this 19 kilohertz signal, which I can again double the frequency of and use for the demodulation of the L minus R prime signal. So this is L minus R with DSPSC modulation. This becomes my composite signal which goes to the FM modulator. So the baseband signal which is going to the FM modulator has a bandwidth of about 38 plus 15, about 53 kilohertz. Not 15 kilohertz with which we started, but 53 kilohertz. Right?
So why don't we use this EM3 filter after this composite signal?
That is because the de-emphasis filter will be used only in this channel at the receiver. We will not be using we will soon see. Let us see the receiver, then it will become clear.
Why you use 19 kilohertz as a pilot?
It will be 10% bandwidth change. 15 kilohertz.
Let me take one question at a time. First question was that why do we use a pilot carrier of 19 kilohertz rather than 38 kilohertz? That is a question. I think the spectral diagram should make it clear. There is a clear separation here. This is 38 minus 15 is how much? 23. So there is a very clean band of 15 to 23 kilohertz which is lying unused. So why not put a pilot carrier where it's relatively easy to filter this out, right? If I put it here, filtering it out will become more complicated because there is also the spectrum of the signal present along with that. Right? So it's much easier to filter it out at the receiver and follow it up with a phase lock loop to acquire this pilot carrier, right? To have a local carrier which is in synchronism with this pilot carrier. It can certainly be done with 38 kilohertz also, but since we have designed this, we design it in such a manner that we get a clean region around 19 kilohertz. Okay, what was your question?
If you instead of 19, 16 kilohertz, we will be saving 10% bandwidth.
Actually, this will, remember, your bandwidth ultimately depends on delta f, right? So delta f will be governed by the amplitude of these frequency components rather than, of course, BT, the transmission bandwidth of the message signal also, the message signal bandwidth also contributes to the overall bandwidth, right? But it's a small fraction, right? So if your peak frequency deviation is 75 kilohertz, so it will become now something like 200 plus kilohertz, right? This is 100 plus, so it almost becomes 250 kilohertz. Yes. Typically, in this consideration, in these broadcasting situations, bandwidth is not of primary concern, right? Bandwidth is not a major concern. Okay. You know, slight 10% bandwidth this way, that way is not a major concern. Now let's look at the receiver, and that will answer some of the questions regarding why the pre-emphasis filter have been used here rather than just before the FM modulator. I think that was the question, right? So if you look at the receiver, it will make it clear. So what do we need to do at the receiver? First of all, we have an FM signal coming in, right? So we have to demodulate this FM signal. After you have demodulated this FM signal, you will get this composite signal with this spectrum, and then we have to separate out the various components, right? That's what we need to do. So for demodulation, we'll use a limiter discriminator. You know, this combination of band pass limiter and FM discriminator that I have just called here, written here, band pass limiter followed by FM discriminator. This combination sometimes is briefly called limiter discriminator, right? This combination. So when you are drawing the diagram in short, instead of drawing so many blocks, you just write a limiter discriminator. But remember what kind of limiter it is. It is a band pass limiter. Okay. So this produces your composite signal here, and now we need to separate them out. How can we separate? How can I get this part alone? By putting a low pass filter. So I have a low pass filter whose bandwidth is around 15 kilohertz. How can I get the pilot carrier? Put a band pass filter around 19 kilohertz, center frequency of 19 kilohertz. So narrow band filter, 19 kilohertz. And finally, this signal again we will pass it through a band pass filter with a pass band of 23 to 53, center frequency of 38 kilohertz. Correct. So you have a second band pass filter whose pass band is 23 to 53 kilohertz. So using these three filters, you can separate out the three components. This we pass through a frequency doubler, right? And this is the input to a synchronous demodulator. Okay, this is followed by your de-emphasis filter, right? And similarly, as far as this channel is concerned, I don't have to do anything else. I got my this L plus R back, right? So I have simply the de-emphasis filter here, and now I got L plus R here and L minus R here, right? And if I want to get L and R, all I have to do is once again add and subtract. So one will give you L, the other will give you R. Okay. For a monophonic receiver, you will not have all this. You will have the FM discriminator followed by the low pass filter followed by the de-emphasis filter.
Questions.
Sure.
So what about in this case we are transmitting just one signal, FM signal. So if we had multiple FM signals, how, does it individually require a different receiver? Because
You want to simplify the receiver design. Imagine trying to design a receiver which simultaneously tries to track two FM signals.
yes sir.
Right? It will be so much more difficult to design such a thing for the receiver. And it's a tunable system. You don't want to make your life very complicated. Receiver design, in a broadcasting environment, you like to make your receiver design very simple. That is
So in
important.
that case, sir, in this case, the filter that we have, so it's tuned to the pilot. So and then only we can
this filter.
Yes, sir.
Yes.
So would the other signal also have the same pilot?
Every one of them, because this is part of their baseband signal. The FM carriers are all different for different signals. One transmitting station has a composite signal of this kind. Another transmitting signal also has a composite signal exactly of the same kind. But the two composite signals are being transmitted using different FM carriers. And totally different, disparate, but there is absolutely nothing overlapping between the two transmissions, isn't it? Because the carrier frequencies in the FM modulator are totally different. I hope you appreciate this point, right? That is, it's like even AM broadcasting. We are transmitting voice and music. They all occupy the same band, but you multiplexing them in different frequencies by using different carrier frequencies. Similarly, also you are using different carrier frequencies. So the composite signal of every stereophonic FM system would be the same, right? There is no difference.
So interfering noise will be higher in that band, 23 to 53 compared to 15.
No. Typically, noise is most common type of noise, as we will see later, will have more or less equal distribution of energy over all frequencies. Right? We call it white noise.
Maybe you think proportional to big FI.
No, noise is not proportional to Fi. What we said was that there is if an interference signal which has a frequency f sub I, a tonal frequency, then the response of the FM discriminator would be such that the higher frequencies will get more amplified. Okay, I think there is an interesting question here because your FM system is working on this, right? And you have an FM discriminator. Whether the de-emphasis filter should be here and the pre-emphasis filter should be just before the transmitter, which is what you had proposed. I think that's another possibility. You can put a pre-emphasis filter here and a de-emphasis filter right after the discriminator. Nothing wrong with that.
In the case of monophonic,
Yes.
how will it extract out everything?
Just the emphasize. If you put the emphasis here. Right. So that's the basic thing. The compatibility requirement is it is for reasons of compatibility requirement that you do things in this manner. Otherwise, ideally, what you're saying is right. I should put the pre-emphasis filter here and the de-emphasis filter, but then it will not be compatible with a monophonic system. Right? Okay.
So, but in that case, you can put two pre-emphasis filters. One at the.
The point is, as far as the monophonic system is concerned, it will have only this chain.
Yes, sir. So even if the pre-emphasis filter, the de-emphasis filter is after discriminator, it will work for monophonic also.
So it won't make him.
There is a difference.
Why?
The monophonic limiter discriminator would have a low pass filter whose bandwidth is 15 kilohertz. This will be followed by a low pass filter corresponding to the message bandwidth, right? and if you what you are saying is have both. Is that what you are saying?
If you were to put it
Saying that
after
the same
distributed discriminator.
same as setup will work for both monophonic
No.
and
The de-emphasis filter is the beginning. It works for
See, the monophonic system does not assume that there is 53 kilohertz bandwidth. It assumes there is only
15.
15 kilohertz bandwidth. So if your de-emphasis filter is supposed to de-emphasize only these higher frequencies, I mean in this relation, there is an incompatibility of some kind, as you can see.
So like the monophonic might have been designed with the pre-emphasis after the low pass filter. So if we are changing design, we have to change design of those monophonics also.
Right. I mean, in that case, there is a change of design required in the monophonic system, which is not permissible when you are designing a compatible system. Right? A compatible system must permit the proper operation of the existing systems, and not a redesigned system. Right? Okay. Anyway, some of the points you raised are very interesting, and one needs to look at those carefully to appreciate all these points. In the rest of today's time, and in continuing in the next class, we will now take up another application, and that application is TV transmission. Okay. So we're now looking at how these various modulation schemes that we have discussed are used in various kinds of communication systems, particularly the most important ones like the broadcasting applications for FM broadcasting and TV broadcasting. So now let's spend some time today on TV broadcasting. Now, as we know, as far as television is concerned, it has to do with transmission of pictures, right? So let's try to develop some basic understanding about the nature of these signals that we like to transmit, okay, and then see what else we need to do. So, okay, for the purpose of discussion, a picture is like a let's say some frame that is given to us, which contains information about the intensity levels or brightness levels of the various elements of the picture. Right? So you can think of a picture as if it has a large number of small little boxes, right, which we call pixels, of which it is composed, right, for the purpose of just I'm just thinking of how to visualize a picture from the point of view of a communication engineer, because we need to understand its features. So let's assume as if this signal, this frame of picture that you have is composed of a grid like that, a fine grid. In the sense that if I want to specify the picture electrically, so ultimately I have to have an electrical representation of this picture, right? An electrical representation of this picture will have to be based on some features of the picture, right? So what we are saying is we assume that the picture has a sequence of brightness levels distributed along this small little this fine grid. So you have some intensity level here, some brightness level here, another one here, another one here, and so on and so forth, right? So if I can capture this sequence of brightness levels both along the horizontal as well as the vertical directions, and represent this sequence of brightness levels in the form of electrical voltages or currents, right, then that would be an appropriate representation for the picture. You appreciate that? So that's one way of visualizing a picture. So you visualize as if it's a frame is composed of, visualize the frame as composed of a large number of picture elements. Of this kind, and these picture elements we call pixels. Okay. Now, it is clear that this number should be large, right. If you want to represent this picture by electrical signal in the as a sequence of brightness levels, the larger the numbers that you select for this representation, the better your picture quality will be. So, there is a the resolution of this picture that you represent, resolution of your representation is a direct function of the pixel size, right, depends on pixel size. Actually, it is proportional to the inverse of the pixel size, right. The smaller your pixel size, the better the resolution. So, I will like that picture better, right. So, if you have to reconstruct based on this representation for the purpose of your eye, you must have a very fine grid. And ultimately, we must convert these picture elements, these brightness levels or gray levels or whatever you like to call them, by a suitable set of electrical signals. If you want to do a color transmission, you must not only capture the brightness level, but also must capture the RBG components of these levels, right, so that you can transmit multiple signals carrying all this information. But let us for the moment discuss only the black and white situation. Okay. Now, you can have when you are working on a computer, it is nice to work like with a grid like this, but in a conventional analog picking up of the picture by using an analog camera, right, you do not exactly do things in this manner. How do you convert a picture into a single electrical signal? You have to scan the picture, right, and the scanning is usually done something like this. You have this frame here, so you move from left to right, right, and pick up the intensities or brightness levels of the various portions of the picture along this line. But as you can see, I do not move in a perfectly horizontal direction, right, in a typical analog system. While I am moving from left to right, I am also slightly moving downwards. So, then I get to the next line by moving again to the left very quickly and keep on moving from left to right again. Again fly back here and keep on moving left to right again. So, that is the typical scanning process. Okay. Typically, we also use what is called interlaced scanning, that reduces the flicker effect significantly. So, that if the first frame starts like that, the next frame starts here and goes like this.
You scan the odd lines and even lines.
You can say that, or you interlace the lines. You interlace in successive frames, the lines are interlaced in this manner. Okay. And the larger the number of lines that you use to pick up the brightness levels, the better your resolution will be, right. So, how many lines to use and how do you exact scanning process will depend on the various. Okay, first let us talk about the scanning process. The scanning process would use some kind of a TV camera, right. And I am not going to go into discussion of various kinds of TV cameras that you can have. There is a variety of TV cameras that you can have. For example, in the good old days, we had the image orthicon tubes, based TV cameras, right, which used an optical system to pick up the brightness level, and then this light was allowed to fall on a cathode, and based on the amount of light that is falling, a certain number of electrons will get generated, right, which were then picked up by a circuit and converted into an electrical signal. That was the basic principle. Today you have more sophisticated charge coupled device kind of cameras, right, CCD cameras. Again, the description of this is outside the scope of this course, so I will just mention these names for you. So, in any case, one of these cameras would convert these scanned lines into a sequence of electrical signals, basically a electrical signal. As you can see, as you are scanning, you are generating a signal as a function of time, isn't it? Some voltage or current as a function of time, continued in the next line, continued in the next line. So basically this entire spatial information is transmitted over a period of time. It's not transmitted instantly, as you can see that. I'm not picking up the picture and transmitting the entire picture in space, right? I'm generating an electrical signal as a function of time. So it will take a finite amount of time to scan this whole picture, and that is the amount of time in which one frame will be transmitted, right? And there will be a certain rate at which you have to transmit frames, so that your eye does not see as if they are disconnected frames, but as a continuous movement, as a continuous picture.
So will
Right.
these lines traversing, will it depend on the size of the screen?
No, it will not depend on the size of the screen. Typically, it will depend on the resolution that you want, right?
So why do we travel at an angle?
I have already answered that question, but let me repeat it again. This is the process of make the process of scanning automatically possible. So what you are doing is, while you are moving, you have to scan the whole picture, right? Either you pick up pixel by pixel somehow, the intensity levels, but in an analog system, it's convenient to, rather than moving like this and then like this, you can't exactly move like that, right? So you move slightly to move a little bit down while you're moving left, and then you quickly move to the left, and keep on doing this, and then at the end of this you move back here, right? So basically, you remember, the scanning process will require some kind of a direction of an of a optical beam. This is an optical beam to traverse the whole thing, right? For traversing, it's convenient like this, rather than in fact that's the only way that you can think of, right? So that you can do both vertical scanning as well as horizontal scanning, right?
So what happens with the time when you're coming back from the end of the row to the start of the next row?
So this is I'm showing you go like
It
this
will go blank, the analog signal will be blank.
during this time.
No sir, between the rows. When you go back to
Here, yeah, you are assuming that this flyback time is very small. So during this time,
shortest kind of thing.
yeah. So okay, let's look at that. These are questions which are anyway coming to. So this scanning is actually done using a system which will make the light beam, which is picking up these intensity levels, or the camera system, to look at these portions of the picture in this manner, right? The camera system has to allow its optical system to pick up first this portion of the picture, then this portion of the picture, and so on and so forth. So it has to be controlled, right? It is controlled through an appropriate sawtooth waveform like this. So the optical beam moves like this. I mean, optical beam moves to make the optical beam move like this. The voltage controlling the movement will move like this, right? And then to make it turn immediately to the left, you have to have a very short time in which to do so, right? I have emphasized that time, but actually that this time by which it just jumps to the left has to be very small, right? And this process will keep on repeating, right? So these are the, you can call, horizontal deflection signals. This is internal to the camera, of course. This process is internal to the camera, right? The camera has a horizontal deflection system which allows this movement of the lines in this particular way, right? And it has also a vertical deflection system. Vertical deflection system has to, so this is as a function of time. What does a vertical deflection system have to do? It has to gradually allow the motion to go downwards, right? The vertical deflection has to gradually, so as the horizontal traversing is going on, there is a vertical, you remember the electromagnetic system in that you have in an oscilloscope, something like that. There is a horizontal deflection system and there is a vertical deflection system, right. So it will have to allow to deflect it gradually downwards. So that's happening at a much slower rate. You know, by the time your horizontal scanning is over, you're only going down a little bit vertically, right. So that's going to happen at a much slower rate than the horizontal deflection rate. So you have a much slower sawtooth waveform going like that, right, and then again at the end of a frame you move like that, you go to the top of the frame, right. So that's a vertical deflection signal. But remember, these are internal to the camera. Okay. So this is how the scanning process will actually occur.
So, but
Yes,
are we
please.
scanning pixels here? Say in the analog system.
Okay, I'm coming to that now. That's the first. Is the scanning process clear? Now the next question is, when we are scanning like this, how do we relate this scanning to this visualization that we had, right? Suppose we have a certain number of lines. How many lines you will use to scan a frame will depend on different standards. For example, as you must have heard of, there is the NTSC standard, right? There is the PAL standard, right? There are one or two more standards, right? So each of these standards specifies a slightly different number of lines per frame. For example, in the NTSC standard, you scan it using 525 lines. So the entire picture is represented in terms of 525 lines. What does it mean? It essentially means that you are dividing the entire vertical region into 525 portions. So which essentially means that 1 by 525th of the total frame vertical size is good enough from the eye point of, from the perception point of view of the eye, right. Now as far as the horizontal scanning is concerned, actually there is no quantization of that kind, right. We are picking all the elements along the horizontal line, right. But from the point of view of trying to calculate, okay, roughly how much is the resolution horizontally and how much is the resolution vertically, we assume that the vertical and the horizontal resolutions are the same, right, because our eye does not have any preferential treatment. That's the assumption here for discriminating vertically or horizontally, right. So basically, so when you say 525 lines, it kind of implies as if you are representing your picture by a 525 into 525 grid. Now this is an implicit assumption, or rather than this is an implied thing based on our scanning process, right? That this implies that this pixel grid has this kind of a composition. We'll start from this point next time. Thank you very much.